Hello everyone, Greg here. How are you today? It's a cold, clammy Sunday day in Oregon in the fall, and it's the way it's going to be here for about 5 months. Didn't get out on my bike yesterday. It was a downpour, so I went into the gym, something I absolutely don't like to do. Spend as many months as I can outdoors on the bike. But we're settled in here. We'll make it through. I don't have a lot to say about last week. The thing that I wanted to clarify is that the purpose of last week was to explore that central limit theorem. And that central limit theorem is what mathematically allows us to create confidence intervals. Now, the mathematical relationship between the central limit theorem and the confidence intervals is rather complex, and one person asked, well, can I calculate a confidence interval by hand? Well, yes, you can. It's quite an exercise in algebra, but of course it can be done. But there's no reason to. The main thing I want you to take away from the week is that the central limit theorem tells us that no matter what the skew of the distribution, so let's say we have a distribution such that the mean is 50, then all possible sample means will distribute themselves normally, and the mean of all possible sample means, that's called the sampling distribution, will have precisely the same mean as the population mean. And that's counterintuitive, but it's very important. The other thing to keep in mind is, what does a 95% confidence interval mean? Well, it means the following. If you took a population and you took all possible samples of 10, so let's say you have 100 values in your population, and you took all possible samples of 10, that would be a lot of samples. But the mean, or the, let me back up my thinking here. The confidence intervals that could be created by all those different samples, of all of them, 95% of the interval would contain the population mean. Not 95% of the samples, 95% of the intervals that the samples create would contain the population mean. So there's a real good little experiment you can do here. If you'd like, let me draw it out for you. Let's say you take 2, 3, 4, 5, 6. Let's say you take the following deck of cards. All right, so you have a 1, 2, 2 3s, 4 4s, 3 5s, 2 6s, and a 7. Now, that is a skewed distribution, and the mean would be right around 4 point something. So that's kind of what we did in the exercise. Now, you only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You only have 13 playing cards there. If you were to take those 13 playing cards and put a number on each one of them, and then find every possible combination of 2, and find the mean of each of those, and create a histogram of those means, you could easily see that that histogram would be normally distributed, and you would have the same mean of means as that population mean. So it's a great activity to do if you're just sitting at the kitchen table one day and your team's lost and you really need something to pick you up. So give it a try, and it'll actually make that concept real. Okay, so looking on to next week. Now, next week there's lots of new things next week. We are really moving into inferential statistics. All right, so next week we're going to be talking about correlation. And let me introduce you to some of the terms that you're going to be using next week. First of all, we have correlation. And correlation is the degree to which variables form a linear relationship. The correlation coefficient is the number that tells you how strong that linear relationship is. You'll also be introduced to the words significance, critical value, p-value, bivariate data, and degrees of freedom. Okay, so let me explain to you just a couple things that we're going to do. Let's say we take a sample of 1, 2, 3, 4, 5, 6 data pairs, and we're going to compare the number of hours somebody studies for the SAT. We're going to take 6 samples, and we're going to take their score of their SAT. Now, it looks like that's a pretty good linear relationship. All right? But we have to have a way to quantify how close those data pairs are to a straight line. That is what the correlation coefficient does. And we have a very nifty calculator to do that, which yields all kinds of other information. So, of course, in a correlation coefficient can range anywhere from -1 to +1, with a -0.5 being a negative pointing down, very weak correlation, and a 0.8 being an upward pointing, very strong correlation. Now, it's important to keep in mind that correlation is different than regression. And the correlation coefficient is not the slope of the line, it's the degree to which the points actually form a linear relationship, irregardless of the slope of the line. So we'll be studying that a lot this week. Now, the next thing that's really important is, let's say we take a correlation, and you say, well, I'm gonna train for the next 6 weeks, get ready for a marathon, and if I train 4 hours, I can run 4 miles. If I train 5 hours next week, I can probably run 5 miles. If I train 6 hours, I could run 7 miles. If I train 7 miles, I could run 6 hours. Now, it's pretty clear that there's a relationship between the amount of hours that you train and the number of hours that you can run. But remember, those are only a sample of data points. And just as we took samples in the last week, correlation coefficients are determined by taking samples. So you're going to be introduced to a new term, and that's called statistical significance. And this is one of the words that people have a lot of trouble with, and it has a very precise mathematical meaning. So when your son comes home and says, "Hey, Mom, guess what? I got on base 4 times today." And you go, "Well, gee, Billy, that's a significant improvement." What you just said is very uplifting, but it really doesn't mean anything. There is a precise mathematical definition for what statistical significance means. And what it means is, if a correlation is significant, it means it's highly likely that that correlation applied to a larger data set based on a sample. Okay, so we're going to start to study the real nuts and bolts of inferential statistics. Statistical significance, critical values, p-values, bivariate data, and degrees of freedom. And the other thing is, this week, when you are creating your correlation coefficients with your data pairs, you will now report your correlation coefficient according to the APA format, and we will show you how to do that. So I haven't looked at too many of the assignments, but this is the week where reporting SEM and reporting statistics that we don't know what they are and that you can't explain are definitely over with. You'll report the correlation coefficient, you'll explain it, and you'll report it in APA format, and we'll explore it a little. And remember that when you go in and you make your post, if others ask you questions, or if I ask you questions, feel free to go in and make another post, or you can fix your post as long as learning is occurring. And if you get any other insights, you're welcome to put that in. So the key is, we've got lots of learning this week before the assignment. I think I'll be here every night this week. You're welcome to call. We will get all caught up by the end of the day, or definitely by tomorrow on the assignments. No problem there. I appreciate your hard work. And so we're headed into the nuts and bolts of it. It's going to get interesting. So stay the course, and hope your team wins today. I looked and it wasn't looking good, so I'm going to go look again. Everybody have a wonderful day. Okay, bye.